Hello guys, in this video we're gonna prove a very important theorem which concerns with linear operators, and the essential idea is somewhat like so if I have a norm space and I have a subspace of this, I have the subspace of it and I call it Y, and now I have an operator which maps objects in Y to a Banach space C. Okay, and I call this operator T. And now what I'm saying is that there exists a unique linear operator from the closure of Y. So if this is Y, and if I add all the limit points of Y, then it becomes the closure of Y. The diagram is very badly drawn, but consider that this is Y, and now I add all the limit points. So this complete thing starting from here, when I add the limit points of Y, is Y bar, and I say that there exists operator from Y bar to my Banach space C with the property that when restricted to objects in Y, so this is Y, and the slightly bigger circle, if you can see it, is Y bar. So if I map objects in my Y, then the operator remains the same. So constricted to Y, T bar constricted to Y is equals to T, and that the norms are equal. Okay, so now we divide it into pieces. Let's look at the first line. So he says that there exists a unique linear operator. What do I need to prove that something exists? How do I prove that it is existing? And the way I do it is by constructing it. So you see, so I just defined this operator T bar. I say that T bar of X is equals to limit n tending to infinity T of xn. And xn is a sequence in Y. Let me draw this diagram again. So if you look at this diagram, you see that there is a space Y, and then I complete the space Y and I write it as Y bar. What do I mean by completing the space Y? I mean that I include Y plus all its limit points. So I have Y bar. And now what do I need to prove existence? Well, in order to prove something exists, I construct it, and this is how I construct it, by this formula. You see? So when I say there exists, in order to prove this existence, I give a formula, and kaboom! Now I prove that its existence. And so again, what is our strategy? A strategy is saying that it exists by defining that operator. Now I have, and this formula, so let me write it down again, limit n tending to infinity xn is equals to x. This formula tells me what xn is. So xn is a sequence in space Y. Okay, now x is in Y bar. Remember, x may or may not be in Y, but x definitely is in Y bar. But xn is definitely in Y. So I define a sequence, a converging sequence, and with the help of this converging sequence, I define this formula. And what do we have now? So since xn is a convergent sequence, it is a Cauchy sequence. And we know that bounded linear operators map Cauchy sequences to Cauchy sequences. So if xn is a Cauchy sequence, then Txn is also a Cauchy sequence. So that is the property of bounded linear operators. They map Cauchy sequences to Cauchy sequences. And the point of writing this formula is that you should be sure that this limit exists. You see, if you're not sure that whether this limit exists or not, then the whole idea is bullshit. And what is inside of this bracket, this whole line, is just a safety check so that we are sure that we are not writing nonsense. And what does it mean? It is essentially saying that this limit exists. So xn was a Cauchy sequence, and we proved that, and we know that bounded linear operators map Cauchy sequences to Cauchy sequences. But since my Z is a Banach space, which means this Cauchy sequence converges to a point in Z. So suppose I write limit n tending to infinity n square. Now, what is this? It's nonsense. It does not mean anything. So I have to make sure that this is not the case here. So that's what I have written in bracket, that that xn is convergent. So that's a quality check that the limit that we have defined here actually do exist, and that we're not writing nonsense. And now, in order to understand this part, so remember, these notes are concise. They assume that you have knowledge of analysis 1, 2, 3, complex analysis, and then function analysis. So each and every line, each and every paragraph is an exploration in itself. So now we are going to explore this part. So I need to prove that this T star is well defined. So let's look at this. So let us look at this in this way. So if I have two different sequences, a sequence xn and a sequence yn, and they converge to the same point. So xn converges to x and yn converges to x. Then I want to show that by well defined, I mean that if this is the case, then let me write it out. Then limit n tending to infinity t xn is equals to t bar x. This is just the definition. This is from above. And another thing, the second part is limit n tending to infinity t of yn is equals to, say, t bar x. Okay, so in order to say that this t bar is well defined, I just need to show that if I have two different sequences which converge to the same x, then indeed these two quantities, you see, let me mark it, see, this and this is indeed the same. Okay, so that's what essentially written here. So if I have a sequence, two sequences that converge to the same x, and now I need to prove that, so in summary, if I have these two sequences, they converge to the same x, then these two limits are the same. This is what I mean that my t bar is well defined. So these sequences may not be the same, but the limit to which they converge is the same. That is what I want to show. It's not obvious as of now. Now, going through these, I see that, again, in our context, this is just xn1 and xn2. And I have the property that the limit n tending to infinity x and 1 is equals to x is equals to limit n tending to infinity x and 2. Now that's the reason why that this thing converges to 0, meaning that if I take limit n tending to infinity, so if I subtract these two things with each other, they would converge to 0. And now since t is continuous, so I have these two quantities. And since t is continuous, I can take the limit out. I would be doing this trick many times during the course of the lectures. So all you need to remember as of now is that if my operator t is continuous, then I can take the limit out. And I know that since t is linear, I can take the t also out. And again, I can put that limit back in, which would give me 0 from here. And that's why now I have proved that. So by doing all of this, I can say that indeed, think of this as an equal to sign now. As a result of this, I can say that indeed these two limits are the same. That's why I can use this formula, and that is why it is well defined. So by well defined, I mean that this property holds. That's why I can use this formula, and this is how I prove this part. So as of now, what do I have? I just know that this t bar that I defined here is well defined. Now the next thing that I need to prove that is t bar is obviously linear with t bar restricted to y is equals to t. Now suppose I take two sequences. I take a sequence xn, it converges to x, and this x is in y bar, and zn it converges to z, this z is in y. So or I should say required to prove. What is required to prove? Required to prove is that t bar z is equals to tz. That is, if now as we can see that t was continuous, so I can write tz is equals to limit n tending to infinity tzn. Why can I write? Since t is continuous. But by definition, I define this to be equal to t bar z. So when my element is constricted to y, then indeed t bar constricted to y is equals to t. So that's my proof right here. And t bar is obviously linear. So in order to prove this, I take a x belonging to y bar, and with this property that if I take a sequence xn in my y and I take the limit of that sequence, which comes out to be x, I can say that norm of txn is less than or equal to norm of xn. This is our standard definition of norm. This is how we define norms. Okay, now I would ask you to take limits on both the sides. So if you take limits on both the sides, then as per my definition, t of xn limit n tending to infinity becomes t bar x, and xn becomes x, because again this is how I defined my x to be. You see here? Okay, now but if I look at this, I can say that my t bar is bounded with norm of t bar less than or equal to norm of t. I get it from here. Now by definition, I see that norm of t is equals to the sup norm of t of x by norm of x, and you see that my x is in y this time. So forget this x. Now we are focusing on an x which just belongs to y, and x of course not equals to 0, as this definition would not hold true or would not make any sense. T bar restricted to y is equal to t. So if my x is in y, then norm of tx is equals to sup norm t bar x. Okay, this is from here. But again, what is this? This is less than or equal to sup norm of t bar x by norm of x. But this time my x is in y bar. You see? And what is this? This is nothing but the definition of norm of t bar. So in one direction I have this, and through the other direction have norm of t less than or equal to norm of t bar, and as a result I have norm of t is equals to norm of t bar. And the last line here proves the uniqueness. So if we go up, we would see that The theorem says there exists. So the theorem says that there exists a unique linear operator. We proved existence here. We proved this property. We proved the norm. And now finally we have to prove that this thing is indeed unique, which means that this T bar is unique. And how would we prove the uniqueness? We would say, okay, suppose that there is a S from y bar to C, and it has the property that S constricted to y is equals to T for every x that belongs to y bar. Now, so we see that limit n tending to infinity xn is equals to x. So let us define my S x now. So since my S is continuous, I can say that Sx is equals to limit n tending to infinity Sxn. This is the standard definition. I would always use this stuff, I would always say that Sx is equals to limit n tending to infinity Sxn if S is continuous. So keep this property in mind. And as we defined here, you can see that this xn, so the transition from here to here might be a bit confusing. So I said that this xn belongs to y, but for elements of y, s constricted to y is nothing but t. So rather than writing s, I can write t. You see, since my element xn is in y, therefore for those elements s constricted to y is equals to t, but that limit n tending to infinity t of x n is nothing but t bar x. So indeed Sx is equals to t bar x, and hence I can prove the uniqueness of my t bar.